In this short video, we'll talk about probability distributions. What is probability distribution and why do we need these distributions? Probability distribution defines the relationship between the outcome of a random process uh, X and the probability of its occurrence, right? So it can be in terms of the probability density function fx or in terms of cumulative probability. But that function or that distribution defines the relationship between the outcome of the random process and its probability. So what is probability distribution? What kind of equation is the probability distribution? Uh, by theory, any equation can be a probability distribution, right? Any equation with its probability value greater or equal to 0 and the integral sum of function from minus infinity to plus infinity, if it is 1, then that can be a probability function. So literally there can be large number of probability distributions and the task is to identify a proper one that fits our requirement. So there can be hundreds, thousands of probability distributions. So any function, if the area under that function from its lowest end to highest end is 1 and the value of the fx or the probability is always more than 0 or equal to 0, then that can be a probability distribution function. Now, why do we want to use the probability distributions? So we always have limited sets of data. For example, if you may have 70 years of total annual rainfall or 40 years of stream flow data. But for design, we need a value of 100-year return period rainfall or a 50-year return period of flood. Even we may have hundreds or 150 years of data, that is only a sample of data from thousands of years, right? So there is an uncertainty on how to extrapolate that value. Okay, so because if you take the only hundreds of data, that's only the sample. It may not, there may be other periods with higher or lower rainfall or discharge, right? So outside that 100 periods. So there is an uncertainty, and to solve this problem, we use probability distributions. So what does that mean? If we can fit our data in one of the distribution, then we can extrapolate the values. That is the main goal, to find rainfall of 100 years of return period using 70 years of data and so on. So these are some of the selected homogeneous probability models that are used in flood frequency analysis based on ARR 2019, Australian rainfall and runoff 2019. So generalized extreme value is one of the distributions. Similarly, Gumbel distribution, log Pearson type 3 distribution, log normal distribution, generalized Pareto distribution, and exponential distribution, right? And you can see the uh, probability density function and the cumulative probability function. So both are defined here, and also what are the moments for different distribution families. We'll talk about the moments, but you can see mean, variance, skewness. These are the moments. Okay. So what are the moments of a distribution? The concept of moment is similar to what we use in statics. The area times distance is the moment. So area under this curve is fx times dx, right? And if you integrate it, you will get the area. And if you multiply that, this is dx. If you multiply that with x, then you will get the moment, right? So area times distance is the moment. So that's what we did here. You multiply with the area with the distance, and you get the moment, right? And this ex, or expected value of x, the first moment is the mean, right? If you calculate this, you will get the mean, which is this value. So mean of the whole distribution is this value. So for if you have the discrete data, so like 70 meter cube per second, 80 meter cubes per second, 30, and then you sum them up and divide by 3, you get the mean. Similarly, for the continuous equation, what you do is you integrate and multiply by x and divide by area, then that will you'll get the mean value. Okay, so that x comes from there. That's the expected value. The next one is once we calculate the mean, then we calculate all the moments from that mean, not from the origin, but from the mean. That means the fx dx times x minus mu, and to the power n. Okay, so if we multiply with 1, you multiply with 2, multiply with 3, so n, you can change the values of n, and then you can get different moments. So moment 2 variance, moment 3 skewness, and moment 4 kurtosis, and so on. So but basically 3 moments are imported: mean, variance, and skewness. So first moment is the measure of central tendency, which means where the mean is, right? So in your distribution, where the mean is. So you have the rainfall data of last 100 years and where that mean is. So if you have the discrete values, you can sum them up, divide by the numbers, you can get the mean. But for the continuous distribution, if you have the continuous equation, then you use this function to calculate the mean. Similarly, variance tells us how the data is spread. Okay, so for example, if there are 3 values, 5, 7, and 9, the mean is 7, but also you may have the 3 values 0, 0, and 21, and still the mean is 7, right? So mean will be 7, but you can see this one is highly equally spread from the mean, whereas this is not, right? So there is a measure of the spread, and that is the variance. Okay, variance defined how the data is spread around the mean. So in some this blue line means all the data are around the mean. So there are some outliers, but most of the data, if you have 100 data, most, and like, let's say if you have 100 data and your mean is 50, most of the data is around 50, and there are some values close to maybe 80, and there are some values close to 20, but most of the data is around 50. But if you look at this one, that means it is more or less equally spread, right? So not highly concentrated at one band at the middle, but it is equally spread. And the other one is the skewness, how the distribution is skewed in one or the other side. Okay, so the middle one is the one without the skewness, whereas this is left skewed data, and this one is right skewed data. Okay, so these are the 3 moments we need to define those different distributions. So mean, variance, and skewness. So once we have these 3 parameters, we can define different distributions. Now, the other concept we need to know is the population and sample, right? Population means all the data. Like, for example, if you want to take the average height of the Australians, right? We need to go and take the height of every single person and then take their height, divide by the numbers, and then we get the mean. Whereas if we take only representative samples, like maybe 10 from Brisbane, 10 from Melbourne, we spread all around different countries, and we take the representative sample, maybe 100 or 1,000 number of data, and then we can calculate the mean. So that is the difference. So when we say the population, that means every single available potential um, data you need to take, whereas when you take the samples means only some of the values. So all the hydrological data that we get are the samples. Like if you have rainfall of 10 years or even 200 years of rainfall data, that is still a sample from the large number of the years. Like you may have like 100, maybe, sorry, thousands or 10,000 years of rainfall in an area, but what we are using is um, only 100 or 200 years of data. So that's the sample. So all the hydrological records, they are the sample data. Okay, and uh, we use this in different texts. You can see different um, notations. So I don't focus on this that much. So in some you write like mu with cap, and some they just use bar and so on. So but basically you need to what I'm trying to say is there are population data and there are sample data in hydrological analysis. The whatever data you get, they are mostly they are the sample data. And from those data, you can calculate the moments, the sample moments. That means for the mean, summation of x divided by the number of data is the mean, right? So it's not the, if we don't use the uh, distribution, but if we just use the data, actual data, from actual data, we can calculate the mean, right? We can calculate the variance from the actual data. Okay, so xi minus mu divided by n minus 1, we can get the variance. Similarly, we can calculate the skewness. So what is the purpose? So we have 70 years or 100 years of data that can be stream flow data or rainfall data, and using that data we calculate the mean of the sample, mean of the rainfall, or mean of the stream flow, similarly variance and skewness of those random variable. Okay, now once you have the mean, variance and skewness of your variable, let's say rainfall, then using those moment mean, variance and skewness, you can fit that in one particular distribution, and then you can define that equation. Okay, yeah, the probability density function or cumulative distribution function. So you can define, and that means once you define that, you can extrapolate for uh, to calculate the probability of any variable, any outcome. Now there are Excel functions to calculate. For example, if you want to calculate mean, you use average. So this is the data. Okay, you have 1 to 6.5. So these are the data, right? And you can use Excel function average to calculate average. To calculate the variance. So variance dot s, you see the variance dot s and variance dot p in the Excel. So we want to use s because that is the sample data. If it is the population data, then you need to use p. Okay, but for sample, you use variance dot s, and similarly for skewness, use skew function in Excel. So you can calculate once you have the data. Here we have 1, 2, 3, 4, 6, 7, 8, 9, 10 years of data. It may be any variable, but you have 10 years of data. And then now we can calculate mu right here. So mu, sigma, and skewness coefficient. Okay, you can calculate all these three using Excel function as well.